And one thing I would be saying to the students is that one programming language doesn't give the best solution for every possible kind of problem. So, for example, when you do the unit root test, the way Walter Enders suggests, uh, Shazam does the job very quick and best way to kind of determine whether the series is stationary or non-stationary. Anyway, so what I'm going to do today is to look at uh, univariate time series. So um, we can divide the time series in terms of univariate and multivariate. And today we are going to focus on the univariate and particularly in the ARIMA. And one of the very important flavor that I'm going to give you today about the univariate time series method is forecasting, right? So like one of the objectives of doing time series work is to forecast like how the data seem to be behaving in the coming future. So, depending on the structure that you have designed for the equation, and then possibly that's the way, the data is going to behave in the coming future as well. Given the trend, given the cyclicality the data has in the past. Okay, so I'm going to share the screen. Right, and I opened my Stata here. You already know like how this data uh, history window, command window, uh, output window, and the detail about the variables will be in what window and all that. So, I mean, all these things you have already seen. So we will not be revising and we'll be directly moving into the time series. So one Excel file that I have forwarded in the email is the data on exchange rate. And the data on exchange rate, along with consumer price index of India and consumer price index of US that I have forwarded you, and then data range from it's always nice to look at the actual file of the data first before you go and work out any econometric estimation. So 1973 till 2023 January. So this is monthly data. And as I was saying, consumer price index of India, consumer price index of US, and exchange rate. Exchange rate is rupees per unit of dollar. And precisely, you must have visualized if you kind of little bit done the open economy or macroeconomic concept in your economics. I'm kind of visualizing, estimating equation, something like purchasing power parity concept, which we define the real exchange rate as EP star upon P. So if purchasing power parity holds, then what we are going to get is EP star upon P is going to be equal to some constant. And if we take the, uh, log or something, I mean, you can depict the equation exchange rate as the function of the domestic consumer price index and the foreign consumer price index. And here, foreign consumer price index, we have taken as US country as the base. So some of those model, when we'll be doing in the ARDL model and co-integration, possibly tomorrow, then we again talk about a little bit of theory and, like how you should be determining and interpreting the results and all that. Right. So you can put this Excel file in your folder where you have put the folder, you have put the data for other classes as well. So this is X rate. This is in Excel file, not even in CSV. You can work out with the CSV file as well. So to start with, let me simply write, import the data, Excel file, go to the browse, then X rate, open. Then these options will be coming, and what we should be interested in is sheet 1 or sheet 2. So sheet 1 gives me
The file
data.
yet.
Sorry?
We don't have the file.
It must have been forwarded to you by Dr. Biro. Just check in your email.
So we just checked our email. I think I have refreshed it quite a few times, but I haven't received the file. I even checked in spam folder.
So let me do one thing. I just forward you immediately in your WhatsApp. Yeah, it's there in WhatsApp as well, right? You can download from WhatsApp.
Okay, thank you, sir.
Yeah. Right. So the first option you can look at, import first row as variable name. So we want the variable names also to be included in this spreadsheet, and that has to be included just to make sure that you know we know what variable is what through the name. Okay, and there is second option. It calls import all data as strings, because we want the data, consumer price index of India and US and exchange rate as a numeric variable. So second option we are not going to click. Date anyway is going to come like a string. So because there are English character is there, so it will be recorded as the string variable only. So if I click OK, then uh, the entire command will be coming like this line, and you can just type ed in the command window and check out this spreadsheet. How does it look like? So first column is date, 1st Jan 1973 till 1st Jan 2023. CPI India, CPI US exchange rate. So we have imported the data. Now, if you wish, you can create a log file if you want all the command that you're giving should be recorded in some format of the file. You should go to the file and log begin, and you can give any name that you want. Let me write E-rate, right? Let me write E-rate, and the extension is going to be .smcl, right? Formatted log.smcl. So I'm going to save it. Yeah. So now whatever the command that you'll be giving will be saved in erate.smcl file. Right. Now further, there is one option you must have been trying to do now. How to create do file, right? So you must have been introduced so far. So I'm not going to introduce in greater detail. So I just clicked the option for the do file, which is this one, right? Just below these statistics, there is a pencil option, like a doc file, right? In the like a doc file, and then new do file editor. So if you click that, uh, the screen will look like this. So one of the problems while you run a regression you'll be facing is that whenever you run a large number of regressions or of any kind, then after running one regression or two regression, stati stops, and you have to click on more options, then it will keep on running. So one of the way to start working is clear all, then set more off, right? Set more off. Let me save it as e-rate dot do file. So extension is yes, do. So extension is also e-rate. Now, login file we have created, we have already imported the data. Next task is to check whether how our time series data is like, right? How is our time series data is like, right? So Right. So if you could see the data here in the spreadsheet as I typed ED, right? So this is 01 Jan JAN 1973, right? So this is how it's been given. So for this kind of data, if it's there, so there are various ways of, like sorting out. So the data can be simply, 0101 1973, right? Then 0102 1973, and so on. So, and or maybe the data has been given in terms of, let's say, 1973 M1, 1973 M2, and so on. So one of the ways to get this data readable and usable, the kind of modeling we are going to do is to write generate T is equal to Tm. This is Tm is Stata inbuilt command, time, and M is for monthly. 1973 M1 plus underscore n minus 1. So if you give this command, then T will be generated, right? Some absolute value type T series will be generated 156 till 756. But fine, month has been recorded. Now, to change the format of the monthly time, you need to write format T percent TM. Okay. So once you do that, then the kind of format we were looking for will be recorded in T. Right, format T percentage TM. Just to cross check, you can just type ED in the command window and go in the spreadsheet and look at, right? So now you can look at separate column has been created for T, which is from 1973 M1 till 2023 M1. So this is the entire data set that we have. Now this is readable, right? This is readable, and this in the variable history you can look at. This is float, right? This is float data. Okay. Will framework. So these internal data time series, right? So this is what you can click, and time variable is T, right? And then since we don't have the panel data, so we will leave that as it is, and then we click on monthly, and then you do okay. Okay. So it's exactly the same thing. So you can operate both ways. Right. Now there is a command. Sometimes you might be required, or sometimes you might not be required. But like sometimes you order the data the way you want it to look like to you. If you are dealing with large data set, then you want out of those large data set and large number of variables. If you're just trying to deal with only first 4 or 5 variables, then you can order the Excel file in terms of order, date, T, right? X rate, CPI, India, CPI, US. And when we write this, what it will do is that it will keep the column for date first, then column for T second, and then exchange rate, CPI in India, and CPI US, and so on, right? Okay. Okay. Now, since we have loaded the exchange rate data here, let's check how the exchange rate plotting look like and what are the basic operations of the time series, right? So first thing to check is plot the graph, right? Plot the graph. All this command you can directly give in the do file as well, and then simultaneously you can run in one go as well. But since we are checking single command at a point of time, and then we are looking at the result as well, how does it look like? So it's good to go in the command, and I'll share the do file later on, just in case if anything you miss out. Okay, so two-way, and in the bracket, TS line, time series line graph, you're basically looking at exchange rate, right? So two-way within the bracket, TS line, exchange rate. Or you can simply write, TS line exchange rate will also do the work. Okay. So this is how this looks like. And in your earlier classes, you might have looked at, like when you produce this in terms of your research work or something, then you can edit it, right? For example, you can look at the x-axis from 1970 M1 to 2020 M1. So like in what interval you want the x-axis should look like, and so on. So, or any mark that you want to give for a particular month, just to capture some fluctuation in some of the years, then you can go and edit as well, right? You can go and edit the graph. There should be edit graph. Yeah, start editing graph. So I'm not going to teach you the start editing graph, which you can do on your own by hit and trial. You can give the title of the work in the x-axis. It's not just the T, but then if you want to write month, for example, or time, if you want to write, you can do so. Right. Now, this is just the exchange rate. Now, the way you plot for exchange rate, and if you want to plot the first difference of the exchange rate, I just click the same command, and then I just write d dot exchange rate. It will be plotting the graph for the first difference of the exchange rate. And when we talk about the first difference, it's exchange rate current period minus exchange rate last period, right? So it will be fluctuating around 0. What you can notice is that there is huge fluctuation around 92. So 92 is one of the years you can figure out when we, like started doing a lot of devaluation, right? And we're trying to move from a fixed exchange rate to managed floating and so on, right? So you'll find fluctuation here, fluctuation around 2008-9. Then fluctuation around 98-99, fluctuation after financial crisis, you find a lot. So, since you can look at there is fluctuation, particularly is quite visible after financial crisis or from financial crisis 2007-8 onwards. So if you want to look for return from the exchange rate investment, you can do some of the Arch and Garch modeling as well. So if you are interested to invest, let's say in Thomas Cook, so you buy $1 today because it's cheaper, and sell it tomorrow when it's costlier tomorrow. So it's just the growth rate of the exchange rate you can, be interested to model, which towards the end, like a glimpse, we'll be looking at the Arch and Garch. Further detail you will be doing on that. Okay. So this is the first difference. In similar fashion, you can look at the second difference. Second difference is just D2, you can D2, D3, and so on, you can do, right? So we'll not be giving the command for everything. Now, if you are interested to plot for lag, right? First lag of the exchange rate. We'll be precisely looking the same thing. So what it is doing is that now the 1970 month 2 is considering the value of the exchange rate of 1970 month one. And that's the way like you have plotted. Okay. So while I'm plotting the graph, you can see this in terms of creating other variable, which is the lag of the variable or the first difference of the variable or forward of the variable as well. Right? So in that case, what you can simply do is gen L exchange rate, lag exchange rate, X rate is equal to L dot X rate. The lag will be created, right? Then lag will be created with this command. You can enter. Anyway, I mean, these are inbuilt commands. So sometimes you might be needing to generate. Sometimes you can directly enter L dot exchange rate, D dot X rate, and so on. There is another command that you can work out rather writing L dot. So we shouldn't be only interested in lag of the variable. We should also be interested in the forward of the variable. So, so those who have studied, again, like I'm repeating it, macro and open economy a bit, then there are trading even with a forward rate as well. And then there is something called forward premium and all that, right? So forward exchange rate is also going to be important when you model the exchange rate. So F, when we say this is the first period forward, right? So the month one, 1973 data is basically considering the exchange rate value of month two. Okay. So that's what the forward is about. In a similar fashion, you can write F2 for the 2-period forward of the exchange rate. So this is just the two-way graph that you can plot. Even if you're not writing two-way, you can simply write TS line exchange rate will be plotting the same graph. So this is how. So how the data look like with other TS line X rate, CPI, India, CPI, US. Let me check how does it look like. Yeah, so if we look at the graph for all the variables together, this is how it looks like. Quite clearly, exchange rate is having positively correlated with consumer price index of India and consumer price index of US, right? So this is, visible way of looking at, like how visibly you can check whether how your variable is behaving, right? After looking at, this plot, what I'm going to look at today is look at the ARIMA modeling, right? And then we'll try to, sorry?
Please repeat this DLF, that command, like D dot X rate, L dot X rate. Kindly repeat that.
You want to see that?
Repeat the meaning you actually mentioned when you are doing case line H rate, X rate, like forward.
So what I said is, like if you want to kind of, let's say, generate the difference of the exchange rate, BX rate, I'm writing, where the new generated variable will be stored, D dot X rate. Okay, so D is basically telling the first difference. And if you write D2 dot exchange rate, that's the second difference, which is YT minus 1, minus YT minus 1 minus YT minus 2. Okay. So if you click or run, then you find Gen the first difference of the exchange rate. And if you want to check like how does it look like, you can cross check in the spreadsheet as well here, right? Lag of the exchange rate and first difference of the exchange rate. In a similar fashion, you can generate for the forward as well. You just write D dot for the difference, L dot for the lag, F dot for the forward. F2, second period forward. L2, 2-period lag. D2, second difference, and likewise. Okay. Now, moving forward, let's model ARIMA. ARIMA modeling, right? So you can keep on writing in the command window. Later on, you can work out in the do file, which later on I'll be sharing with you as well. Okay. So, I hope every one of you have read how the theory on ARIMA looks like. So, just to give you brief glimpse. Right? ARIMA, or what you call ARMA. So first work that you do is identification. So what do you identify here? What you call is P, D, Q. So when you run a regression, YT, so like you want to estimate Y in a univariate setup, then whether its first lag is going to be important or not is basically checking lag P, which is the first lag of the autoregressive process. YT minus 1 is autoregressive process of 1 that you can visualize. Secondly, whether the error term that you get is delta is equal to delta epsilon t minus 1 plus Vt. What we are saying here is that whether the lag of the error term is also determining the residual. So this is going to be Q, and whether Q is equal to 1. And when the series YT here is non-stationary, then the first thing that we try is take the first difference. And taking the first difference of Y can make the data stationary, or it might not be stationary. But then in most of the cases, in measure macroeconomic variables and financial data, first difference give you this stationary series. So if the first difference is giving YT to be stationary, then in that case, D is going to be equal to 1. And in this case, if it's AR1, MA1, and D is equal to 1, then this will call ARIMA 1, 1, 1, right? And order of integration is 1, right? Order of integration is 1. So this is how the identification we work out. In detail, you can pick up any standard book on time series and you can find all these things. If you're finding difficulties in understanding, at least you can start with Gujarati. First, identification, then second, estimation. Right? You estimate the ARIMA that you have picked up from here. One thing you need to keep in mind is that when you estimate, when you are estimating, in ARIMA model, you can try your best to pick up the best possible model which is fitting your data, which is not only good in terms of fitting your data, but also good in terms of forecasting the data as well, which can be relevant for the variable which you are interested in. Or maybe you can tell your boss that the cell is going to go up or going to go down in the coming future, and accordingly your boss can decide to increase the number of units to be produced or not, right? So estimation is the second one. So you model different variation of ARIMA, right? So this is just one method we have talked about. Other can be 101 if it is stationary in the level, or it can be 1 1 0 0 1 1, etc. Okay, so this is how you can work out in the ARIMA. We'll do some of this variation. Third is diagnostic checking. What you do in diagnostic checking is whether the kind of ARIMA modeling that you have considered is giving the residual to be white noise or not. So here you deploy different kind of testing for the residual, and then you try to find out whether residual is white noise or not. And if it's white noise, then that ARIMA model can be considered to be a good fit for fitting the data and for the forecasting as well. However, one model you can consider to be the best fit, but then when you start forecasting, it's not necessary that that model is also going to perform really well in terms of forecasting as well. So keep that in mind. Okay. Then fourth, like when you just want to fit the data, then first, second, third is enough. But very often, ARIMA model, which is very famous which is very famous for, is forecasting, right? In most of the cases, we use the ARIMA model for forecasting purposes, right? Fourth is forecasting. And all these four procedures we are going to do. Okay. Let's start. So, how one way to check whether just a moment. Yeah. So the first thing that we do is stationarity test. Stationarity star I'm putting because this is just the comment. Stationarity of the data. Right, in the stationarity of the data, there are statistical way to test this stationarity, which is Dickey-Fuller or augmented Dickey-Fuller, we call. And there are various other tests, Phillips-Perron, KPSS, NG-Perron, right, etc. However, like here in ARIMA modeling, we are interested into PICA, P and Q and D, which is order of integration. So definitely statistical test will be doing. But before we proceed with the statistical test, let's look at the correlogram. Correlogram. CORRGRM X rate. So we are just dealing with univariate time series model for exchange rate only. We are not taking CPI India and CPI US for the time being. Okay. Correlogram X rate. So when you run the command, you can check lag is being considered from 1st to 40. This is by default Stata gives because we have around 600 observations. Okay, we have around 600 observations. So here the autocorrelation, parallelogram is checking till 40th lag. And what do you notice? This AC is the autocorrelation function. EAC is the partial autocorrelation function. Q is the box Pierce Q statistics. So what we want to do here is that we want to observe like how these spikes are looking like, right? So these spikes for autocorrelation, right? This is the value has been given, and this is the plotting of the rows. So what you notice is that spikes are not decaying down very fast. Okay, which spikes are not decaying down very fast. So the data is non-stationary. That's what we say. Here, only first lag and second lag spikes seems to be important. Rather, after first lag, second spikes is really, really small. So in terms of selecting PDNQ, you should not be going beyond AR2 or MA2, right? You should not be going beyond AR2 and MA2. That's one information we can collect from here. Box Pierce, when you look at the null hypothesis in the case of Box Pierce is the autocorrelation value at different lags are 0. And since these are the p-value given, which is 0 or close to 0, so you reject the null that all those serial correlation are 0. Right? It means the correlation are significantly different from 0 is the conclusion. Individually as well, you can check SC, X rate, right? So you can check it out. This shadow part you can look at is the 95% confidence interval. And what you notice is that these spikes are not, dying down very fast and not even within 95% interval. So this is non-stationary. Similarly, you check PAC, partial autocorrelation of the X rate. Right? The way we looked at in the CoreGram command, first spikes and second spikes. These are the only two spikes which are significantly out from these shaded regions of the 95% interval. There are other spikes as well, but those are small. So first and second lag of AR and MA should work out good. So this is the graphical way of observing the behavior of the time series. Now, we can also be interested to look at how does the statistical test look like, and the detailed about statistical tests of stationarity and non-stationarity from the language of Enders, I'll be telling towards the end of ARIMA, because that is going to be more useful for ARDL and ARDL approach and co-integration model. So right now, I'll be just simply testing the statistical test in a simple way. So ADF test. So ADF test, let's do ADF tests. And just to give you a glimpse, so the way equation can be expressed is the way you can look at an equation number 1, right? So when you include the pth lag, difference of the pth lag, then basically you are considering lag, meaning second period to pth period. Then it's called augmented decay fluid. Otherwise, if you exclude, and if you're just dealing with the first lag, that's going to call the decay fluid, right? Simple decay fluid. So what it does is that you start with the most general model, including the drift term and the trend term in equation 1. And if you find data to be non-stationary in equation 1, you go and check equation number 2 without trend, but with drift. Okay, and again you find data to be non-stationary here, you go and check in equation number 3, which is without trend and without drift. Drift, when I'm calling it's precisely the constant term or intercept term. So if you declare the data to be non-stationary, even in the case of equation number 3, then you declare that the series is non-stationary. This is the way to do by the Walter and us. Okay. In detail, I'll be telling you about, like how testing can be done, which is tau test and phi 3 and phi 2 and tau mu. A little bit of econometrics. Otherwise, without understanding this, it will be difficult to follow the non-stationarity of the series, whether you're getting it or not. And where should you introduce the series like a level variable, and where should you introduce the variable like a first difference? Okay, so I'll be telling you a little bit about it again towards the end of Arima. Fine. What I'm going to do is simple decay fluid test, decay fluid, X rate, comma, trend, regress, lags, right? Lags, for the time being, let me just consider 0, right? You run it. So we need to consider the equation first with trend and intercept, trend and constant. Okay. What you will notice is that this Mackinac approximate p-value is 0.7341 and test statistics is minus 1.738. Right. So p-value is really, really high. So you do not reject the null. What is null? Null is random walk with or without drift. Null is random walk, meaning null is non-stationary, meaning it has unit root. Keep in mind, different programming language keep the null hypothesis differently. If you work out in eViews, null hypothesis will be no unit root, right? In eViews, null hypothesis is going to be no unit root. In Stata, null hypothesis is unit root. So be careful while you decide about stationarity and non-stationarity, the way programming language is working and the kind of results it's giving. Okay. So series is non-stationary, fine. With trend. Now we run the regression equation second with drift. Drift. Consider for the time being lag as 0. I'm going to tell you the importance of lag as well in a while. But for the time being, let's just run the stationarity test. Decay fluid, X rate, drift, regress, lag 0. In this case, also you find p-value to be really, really high. Test statistics is 1.504. You do not reject the null of the random walk or null of the non-stationary. Okay. So that's the second one. Let's run the third regression. That should be without constant and without trend. So let me write no constant. So in this case, what do you find? The test statistics is 4.57. The critical values are, negative minus 2.58. So basically, the test statistic value to the right side of the critical value. So these unit root tests are one-tailed tests, which you can again check for detailed understanding. Again, here, even in this case, you do not reject the null of random walk. So yes, data is non-stationary. So once you declare the data is non-stationary with a model with trend and drift, without trend but with drift, in the second equation, and in third equation, without trend, without drift. And when you find non-stationarity in all these three cases, you declare that the series is non-stationary. But then anywhere in between, if you find the data to be stationary, then you declare the data to be stationary and you stop there. Okay. So for example, in the second regression equation itself, if you would have found the series to be stationary and not random walk, you should have stayed there itself. You stopped there itself. You should not check for the third regression without trend, without drift for non-stationarity, right? Okay, so that's the way to deal with stationarity and non-stationarity. Fine. I'm going to tell about the importance of lag. Since we are dealing with 600 observations, normally, you know, if you talk about different books have different way of dealing with. Some of the books say it is that lag maximum you can consider is 1/3 of the total observation or 1/4 of the total observation, right? So when we talk about 1/4, it's going to be more than 100, considering considering 600 observations. 1/3 is further going to be higher. However, even if you're dealing with a large data, large number of observations, considering large number of lags, it should be a point of worry for you. Why should it be point of worry for you? Because including large number of lags in the equation will be eat out a lot of degrees of freedom. And when it eats out lots of degrees of freedom, then the reliability of the tests will be lesser. Okay, some of these basic concepts you have learned in your basic econometric text. Okay, so we should be, right now, let's just figure out some random numbers with lag. So you can start with the model with drift and trend. Let's start with 10 lag, right? 10 lag, right? And you can check whether what are the lags which are significant, right? For example, lag 6, lag 7 are not significant. Lag 8 is not significant. Lag 9 is not significant, right? However, from lag 1 to lag 5 is significant. So a priori, it's clear that taking till lag 5 is kind of okay. Taking till lag 5 is kind of okay. Again, like we are trying to do some kind of approximation. You can keep on increasing number of lags, 11, 12. So even if it's 6, 7, 8, 9, 10 are not significant, there might be some a lag at 15th or 20th can be significant. But, like some of those uh, minor error keep on coming. But what consistently what we can look at here is lag 1 to lag 5 are significant. So here, one of the command that you need to give is estat IC, right? You check the AIC here, right? You note it down in the Excel file. For lag 10, this is the AIC, this is the BIC. And these are the significant results in lag 1, lag 2, and lag 4, and so on. Then you run a regression of this Dickey-Fuller with 9th lag, and E stat IC. So this way, you keep on running a regression from 10th lag to lag 0. And you check in what lag AIC and SBC is minimum. Sorry, AIC and BIC is minimum in this case, right? At what lag AIC and BIC is minimum. So consider that lag which is giving you the minimum AIC and BIC and test the non-stationarity. Okay, that's like the optimal lag selection that you are doing. So while we do all these things manually, EViews it has a little faster way of doing the lag selection criteria. What Shazam does is that it gives you Shazam iterate by itself and will tell you which lag you should consider. Okay, so Shazam will be iterating by itself and then will tell you, okay, select this lag and then go for the non-stationarity test. EViews you will have to do, but it's smarter way of doing. Stata you have to do manually for each lag. Okay, so that's the little bit of difference. You can check it out with other programming languages as well. Okay, so what we notice is that first lag is non-stationary at 0 lag. So I'm not going to check here the optimal lag, but we can keep on going with lag 5 because lag 5 we found to be significant in terms of statistical test as the first observation. You can cross-check whether AIC and BIC is minimum with the fifth lag as well, considering the lag from 0 to 10. Okay. Now,
Excuse me, sir.
yeah.
So what should be a starting point? We should start from 10 lakhs or 12 lakhs for monthly data.
So actually, the starting point is, you start with 0 and then 1 and then 2 and then 3 and 4. Different econometricians have different way of doing it. So I started with 10, assuming that, randomly just to figure out till where we are finding out our lags are coming out to be significant. So 10, I mean, we found that 6, 7, 8, 9, 10 are not significant. So it's not a nice idea to go beyond 10. Okay. So if you start with 12, let's just check 12. How does it look like? Yeah, it's not significant beyond 5.
So can we use the AIC method?
You can randomly select. And, since yeah, so Rashmi has a question. Which type of series should be used for checking stationarity? Is it raw series or log of a series? Yeah, that's a very nice question. So exchange rate when you took, right? We plot the graph. Clearly, it's continuously increasing, right? It's trended non-stationary. Exchange rate is trended non-stationary. Now, you can work out with non-stationarity checking with the level variable itself. But what happens sometimes when you take the log of the exchange rate, sometimes many of those non-stationarity, vanishes. So it's nice idea to check. It's nice idea to check the non-stationarity with the log of the exchange rate. So that's a nice question, and why we should also be, considering. Just a moment. So R, which is real exchange rate, is AP star upon P. where E is the nominal exchange rate, P star is the consumer price index of US, consumer price index of India is P. So when you take the log of it, or when you consider the purchasing power parity concept, what do we say? EP star upon P should be 1, some constant, and that constant let's assume to be 1. So if you take the log of this, what we get is log of E is equal to, or log of E plus log of P star minus log of P is equal to 1, right? Which you further re-express. Just a moment. Which you can further re-express this equation as log of E is equal to log of P minus log of P star. Sorry, this is going to be 0, right? So log of E is equal to log of P minus log of P star. This is the kind of equation you might be interested to estimate, which you can think in terms of, beta 0 plus beta 1 log of P minus, or for the time being, let's write it plus beta 2 log of P star. Okay, so many of the occasions, it's always better to take the log of the financial variables and macro variables because it reduces a lot of problems in terms of known stationarity or what you also call serial correlation or heteroscedasticity. And after forecasting, you can always, create an exponential of that series, and then you'll be getting the level variable, which is the actual variable that you should be interested in. I hope it's clear.
Right. So can we use the AIC method also on deciding the optimum lag?
Sorry.
Can we use the AIC method also for deciding the optimal lags for the Dickey-Fuller test?
Yes. Yeah, so sometimes AIC and BIC give conflicting result as well. One will be saying lag 5, another will be saying lag 6. In that case, you have to go with one, right? Either AIC or BIC. So very often, econometrician just go with AIC.
And in AIC method, you have to also specify how many lags they should consider first in the formula, like from 1 to 12 or 24. So what should be the optimal number that we should enter in that for lags?
Yeah, so that's what I'm saying. This is where, you find different books will be saying econometrics is an art. So I randomly started with 10. So, other thing which, again, you can logically say is that univariate time series data is good for estimation and forecasting if you have less number of observations. So let's say you just have 50 observations or 100 observations. In other words, what I'm saying is that we have 600 observations. That shouldn't be really nice for forecasting the exchange rate beyond 2023. Why? Because ARIMA is fitting all the data all the way from 1973 month 1 till to 2023 month 1. And there might be different economic events in between which will be affecting the ARIMA estimation. So to capture the proper forecasting and fitting of the data, last 100 observation consideration can be a fine idea. And that's normally, very often different econometricians do. So 100 observations, 150 observations. So 1/3 of the 100 observation is going to be 30 around, or 1/4 is going to be 25 around. That's normally way to check the autocorrelation function and partial autocorrelation function. At what lag, the spike is basically dying down, right? In the case of Dickey-Fuller, you say is that what lag it is significant, and AIC is also minimum. So this is just a random way of checking. Normally, even if you're dealing with 100 observations, we do not necessarily have to go till 25th or 30th observations. Okay, sometimes it works up till 10th lag is fine, right? Checking till 10th lag is fine. I mean, तब तक रिजल्ट पता चल जाता है, रिजल्ट आ जाता है वहां उतना करने की जरूरत नहीं पड़ती है. I hope it's clear.
What if the 10th lag is optimal? It is coming
Sorry?
to be significant. What if the 10th lag is coming to be significant? So we should increase the number of lags.
Yes, you should check for 11th, you should check for 12th as well, as long as you are dealing with large number of observations.
Okay, thank you, sir.
If you do not have the large number of observations, let's say you're just dealing with 25 observations, then including 10th lag is really, really big. Then immediately, critic will be coming with a question saying is that this is going to make your degrees of freedom really, really low. So if you could recall the variance of the error term in a normal regression, what do you find? T statistics is equal to beta hat divided by standard error of the beta hat. Standard error of the beta hat is square root of the variance of beta hat, right? Variance of beta hat is sigma square divided by sigma xi square. So sigma square, the way you define, you will find sigma square is equal to summation ut hat square divided by n minus 2, right? So when number of observations, number of lags you are increasing, the number of parameters to be estimated will be going up. It means 2 is going to be n minus 10. So n minus 2 is bigger than n minus 10, right? So n minus 2 is smaller, and when this is smaller, what it is going to do is that sigma square will be smaller. And when sigma square is smaller, variance of beta hat is actually sigma hat square divided by summation xi square. And if this is going to go down, variance will be smaller, and variance is smaller, meaning when you do the t-test, beta hat divided by standard error of beta hat, this is going to go down. It means these statistics will show unnecessarily insignificant. Okay, these statistics will be going up when you are increasing large number of observations as lag. So even if the t statistics in real world is not significant, this will show significant because large number of lag when you include. Okay, some of this logic, you can infer from simple regression equation. I hope I could clear the doubt.
Yes, sir. Thank you.
Yeah. Okay. Moving forward from beyond, let's say, Dickey-Fuller and FEF and PSE, in terms of identification, we found that partial autocorrelation is cutting. Spikes is cutting at first lag and the second lag. So we are not going beyond AR1 and AR2 and MA2. Okay. So the way we do the test for the Dickey-Fuller, similarly, there is another test called Phillips-Perron. And Phillips-Perron is little stricter than augmented Dickey-Fuller. So I'm not going to talk about in detail about the Phillips-Perron now. You can check what are the importance of Phillips-Perron. So what happens normally is that even if you find that the series is non-stationary, in the case of Dickey-Fuller, Phillips-Perron will be saying stationary. Okay, so in that sense, this is stricter. In that sense, it's stricter in terms of results. But statistically, you need to check in what sense Phillips-Perron test is stricter. So Phillips-Perron test is another test of non-stationarity you can cross-check. Okay, I'm not going to talk about the Phillips theorem. And there are tests like Kwiatkowski, Phillips, Smith, Chin test. That is what we call KPSS test, etc. I mean, and there are, like time series modeling has become much more complicated now than we could imagine a few years back. So now what authors have also started doing is, suppose there is structural break in the equation, and because of that structural break, series could be non-stationary. Okay, so how do you incorporate that structural break in the equation while testing for non-stationarity? So some of those new tests have come up. So while checking for non-stationarity, you shouldn't just be, going and go and check the Dickey-Fuller and Phillips curve. You should also be worried about whether there is structural break somewhere in between, and whether Dickey-Fuller at all is appropriate to test in this case or not, right? So some of those things, a little bit of advanced level, you can check. And a standard way of cross-checking the structural break is Goldfeld quant test. And again, you guys are in the age of internet revolution. So uh, uh, this programming, etc., is not rocket science. I mean, any doubt or any problem you find, you simply look out in the Google, and all the information is available. It will connect to California University. It will be connecting to Princeton, and then there are a lot of programming given, and one can easily do all this programming. There is no rocket science. I'm repeating. Okay. Okay. Now let's start modeling ARIMA and do a little bit of forecasting. Just give me a moment. Right. So estimate ARIMA model. Estimate ARIMA model. ARIMA X rate AR1 no constant. You might be interested to include the constant only if it is improving in terms of AIC and BIC. Otherwise, normally constant term is not really included, right? So this is ARIMA modeling of 100. So you can, sorry. ARIMA 100. So what are we doing? We are, okay, so the first difference, we found data to be, okay, so the first difference we haven't checked. So first difference, you can cross-check. I mean, first difference normally is stationary in time series data. And as one of the participants was asking question whether dealing with log is fine. I mean, so far I'm dealing with the level variable itself. You can deal with the log or level variable in any case. Uh, that's fine. I mean, it's your way of dealing, but I'm repeating it again. So taking log is a nice idea. I have not taken in my case. Okay. So ARIMA 100, or you can call it. Okay. So ARIMA 100. Let me call it. So the first variation of the ARIMA modeling we are doing, ARIMA X rate AR1, no constant. Okay. So you ran it, you check first lag is highly significant with Z statistics to be 7070. Sigma is highly significant. So let's look at the other variation, which you can call it MA1, no constant. This is also highly significant. So first lag in both the cases are perfectly fine. What model that should be fitting more accurately in our case so far from the statistical results is that ARIMA D dot exchange rate, right? D dot X rate. Why? Because we think that the first difference is going to be stationary. So D dot X rate, and we write it here, ARIMA. This is another way of writing. ARIMA 1, 1, 1. Okay. So P is first, Q is first, and order of integration is 1. Run it. And what you notice is that MA1 is not significant. AR1 is significant. Okay, so what are we doing? We are cross-checking the variation of it, right? So 1, 1, 1 doesn't work to be fine. So let me call it 1, 1, 0. Fine. So we are not going by 1, 1, 0. Sorry, 1, 1, 1. We are going by 1, 1, 0. Now 1, 1, 0 seems to be fine, but here the lag seems to be fine. Constant is not significant. You can suppress constant by writing no constant. That's okay. Let me write 2, 2, 1, 1 and check. So yeah, coefficient for MA is not coming at all. So AR 1 and 2 is coming out to be significant. So it's still fine. So 2, 1, 0 might be more appropriate. 2, 1, 0 might be more appropriate. Cross check 3. Yeah. So AR1, AR2, AR3, all of them are significant. Okay, these variations you can cross-check and look at what are the lags which are significant, and till that lag you should be going and check and shortlist around 3 to 4 or 5, 6 ARIMA models for comparison purposes. I mean, in all these 4, 5 ARIMA model which you are shortlisting, you'll be using those ARIMA models for forecasting purposes. And when you use those models for forecasting purposes, before forecasting, you need to check whether white noise is coming out or not. I mean, residual is white noise or not in those ARIMA models. Okay. Okay. So some of this variation we check. This is, in the beginning, the kind of ARIMA command we have given is different than the ARIMA command that we have given now. There is slight variation of this command as well. For example, this ARIMA D dot exchange rate, you can write it as AR 1, 2, 3, and you can write MA 0. MA 0, or if you want to consider MA to be 1, you can consider that. But MA 0 is not necessarily required to write, because considering 0 meaning you are not interested in the coefficient for the MA process. So it will not even be giving result perhaps. Yes, it's not going to give you the result. But then the moment you call it MA is equal to MA is 1, it will be giving the result. Okay. Yeah. And now what you find is that MA is coming out to be significant. Constant is significant. It will be the same result though. It's wrong. 310. And this is 310. It should be giving the same result. 311. Eight minus 2, 1. If we write this to be exchange rate, so it's a small typo here. When we run ARIMA X rate, ARIMA 3110, meaning this is integration of order 1. So the first difference will be considered. Now, when we look at this, then we should D dot X rate AR 1, 2, 3 and MA1. Let's check out the coefficient now. Yeah, it's exactly the same. So it's a slight mistake here. So when you run a regression, ARIMA modeling basically, ARIMA X rate, ARIMA 311. We do not consider the D here, right? Because since 1 has been considered here as the order of integration, so it means the first difference is being considered for the series. In a similar fashion, since here we are not separately inserting the order of integration, so here it has to be ARIMA D dot X rate, has to be there. D dot X rate. Anyway, these are a slight variation of the model. Now, when you work out with this slight variation of the ARIMA model as well, for each of these models, you need to cross-check. You need to cross-check the AIC and BIC. Okay, so let me write the model this way: ARIMA X rate, ARIMA 311. Okay, run it, and let me write ESTAT IC. So you find 1201 and 1228. Okay. Now, slight variation of this model, you can cross-check 211. EStat IC 1200.749. So 211 is giving better result in terms of AIC. Okay, 211 is giving better result in terms of AIC. You look at BIC, 1222, 1228. Both in terms of AIC and BIC, ARIMA X rate, ARIMA 211 seems to be better. Now, this is one of the diagnostic checking that you do, right? So you are selecting the ARIMA model, and while selecting the ARIMA model, while including the lags or ARIMA lags, AR lag, MA lag, you look at the significant. At the same time, you also check whether like in which case the AIC and BIC is giving the lower values, and accordingly you select that. More importantly than this, after running a regression, ARIMA estimation, one of the very important tests that one had to do is whether the residual from this model is white noise or not. And when we say white noise, meaning constant variance and expectation of the error term should be 0. Okay, that's what the white noise means. Okay, so run this regression again, and let me write that command, which is the command for white noise. Just a moment. Okay, so yeah, that calls WNTESTQ. WNTESTQ. Okay, so sorry, just a moment. Before we test this, we need to restore. We need to restore the residual, and to store the residual, you need to write predict E1, which is the error 1 name that we are giving, residual. So residual is being saved. Residuals is being saved in E1. Okay. So E1 has been generated. Now this E1 is whether white noise or not. You can check W. So this is Porte-Montu test that we call WNTESTQ E1 over lags. Some random lags that you can select. But here, AR model maximum has gone till 3. So let's just cross check with 3. What do you find? What they want to test for? White noise. Q statistics is 0.28. P-value is really, really high. So null hypothesis. There should be a null hypothesis. Oh, sorry. So null hypothesis in this case is no serial correlation. No serial correlation of the residual. So you do not reject the null, right? Since you do not reject the null because P value is really, really high, Q value is really, really less. So you do not reject the null of no serial correlation, and white noise meaning no serial correlation, mean had to be constant, and on average, the residual should be 0. So yes, this model is having residual as the white noise. So this model definitely we are going to select as 1. So ARIMA 311. Now, the way you test the white noise test for this equation. Similarly, you can check for autocorrelation function of E1 or what you call choregram E1. Yeah. So what you find is that now series is kind of, residual is kind of stationary. You see, autocorrelation value is very less, close to 0. Partial autocorrelation value is also very less, close to 0. Q statistics now gradually increasing with lag. It's not significant till 16th lag. So this is Box-Pierce Q statistics. What it says is that squared of the correlation of the pth lag is 0. So first lag, autocorrelation is square of this period to last period, autocorrelation from last period to last period, and so on. Simultaneously, all of them is squared to be is equal to 0, that we say. In other words, in terms of looking at the spikes in autocorrelation and partial autocorrelation, what you find is there is no spikes beyond 95% of the interval. So rightly, even with autocorrelation function, partial autocorrelation function, you can say that residual has a white noise. So this is what you do with 311. In a similar fashion, you can check for ARIMA 211 as well. ARIMA 211 as well, right? So run it. Predict E2, predict E2 residuals. Then you write WNT ESTQ E2 comma lags 2. Yeah, this is also telling white noise. So both the models are white noise. Both the models are giving white noise residual. So at least, 2 models we have selected. As I have been saying, you can select many models to compare across. Okay. Now, one of the tasks of modeling ARIMA is to forecast, right? And there are different way of looking at the forecasting. So before I tell you about the forecasted values, let me brief you, right? So when you have the data, let's say Y, from Y1 till Y20. So what you do while forecasting, so 3 stages we have already crossed, right? So diagnostic checking in the ARIMA, then, identification, estimation, and diagnostic checking. All these 3 stages we have already crossed. And after crossing all these 3 stages, we have selected 2 models of ARIMA 211, ARIMA 311. Now from these 2 models, one of the tasks that we can do is forecast. And forecast, when we work out, there is something called in-sample forecasting, and there is out-of-sample forecasting. Right? Out-of-sample forecasting. Now, in-sample forecasting means what? One way to look at is, regress. Sorry. So when we are writing ARIMA X rate ARIMA 211, right? This is fitting the data from observation 1 to 20. When you write predict just a moment. Okay. Predict X rate underscore P1. If this is the command you give, then this is giving the prediction of the in-sample forecasting. So there is actual values of Y1 to Y20. Now this is giving you Y hat, which will be Y1 hat till Y20 hat. So ET hat, when you try to derive, what you do is Y1 minus Y1 hat and so on. So this is in-sample forecasting, right? This is in-sample forecasting. Now, another example of the in-sample forecasting is before going for out-of-sample forecasting, what you need to do is you need to restrict these observations from Y1 till Y15 as the estimation period. As the estimation period. And remaining Y16 till Y20 as the period of forecast. This is again in-sample forecasting. Why? Because we already have the data available from Y1 to Y20. But what are we going to do now is we are going to check whether forecasting by ARIMA 211 or ARIMA 311 is better in sample forecasting. So we will be using ARIMA 211 here, ARIMA 311 here, and we will check in terms of in-sample forecasting which one is doing better. Depending on which one is doing better, accordingly we will decide to forecast out of sample, considering the model which is giving you better in-sample forecasting. So before doing out of sample forecasting, what you do is you divide the in-sample forecasting this way. Okay, you divide the in-sample forecasting this way and forecast for Y16 to Y20 using this method and then using 311 and finding out which one is giving the least error, this one or this one. Since you will be dealing with more than 2 ARIMA models, maybe like 5 to 6 ARIMA models you are dealing with, and you find that, you know, 1 or 2 models of those models are giving you least error in terms of in-sample forecasting. So precisely those 2 models are assumed to be giving a best forecasting results. That's what precisely you are trying to figure out for the time being. Fine, but you should not just be sticking yourself with these models, 2 models only, which are giving the best in-sample forecasting. You should forecast with all those additional 3-4 models as well. And you know, you can compare whether these models which are giving the best in-sample forecasting are still giving best out-of-sample forecasting as well or not. So that's why considering additional ARIMA models are also a nice way to look at it. Okay. One more thing I need to tell you here is that when you consider the variable y, which is y1 till y20, and when you consider the observation for in-sample forecasting from y1 to y15, what you're doing is that first period ahead forecast, right? First period ahead forecast is basically you'll be getting the value from y16 hat till Y20. Second period ahead forecast. So when you call it second period ahead forecast, the value or the estimation that you will be doing is still Y1 to Y16. So the forecasted value that you're going to get is Y17 hat till Y20. Third period ahead forecast, you'll be estimating till period 1st to 17. So the values that you're going to get is Y18 to Y20. Accordingly, now these are the first period ahead forecast. So you will be collecting these terms and will be creating a new column. So this value you put as the first one, this value you put as the second one, this value you put as this third one. So this is basically the first period ahead forecast. The second value, which is going to be Y17, Y18 here, Y19 here, is going to be the second period ahead forecast, third period ahead forecast, and so on. Now, what you do is that you compare this first period ahead forecasted value with the original value of Y16 to Y20. Similarly, you compare the second period ahead forecast value with Y17 to Y20. And likewise, find out the residual sum of square, root mean, percentage squared error, and so forth. There are various ways of evaluating the in-sample forecasting. What you do is a root mean squared error, root mean square, root mean percentage error, something like this, right? There is, so this would be RMSPE perhaps, RM, root mean squared percentage error. There is Theil coefficient, right? So there are various ways of selecting the model in terms of forecasting capability. Okay, so this is how you actually work out, and everything cannot be done in this data. Some of these things you work out in the Excel file, right? And once you do in the Excel file, you bring it back again in this data in terms of evaluating the forecasting evaluation that we got, forecasting evaluation, right? And once you complete this forecasting evaluation in sample forecasting, the next task is to do the out of sample forecasting. Okay. So some of this work you need to do in the Excel file, which I cannot show in how you can do in the Excel file, because there has to be separate workshop for forecasting separately, because this is more to do with time series modeling and all that. But you know, forecasting is one of the essential part of ARIMA and univariate modeling. So I had to give this glimpse. And once you are thorough with estimation and forecasting in sample, out of sample, exactly the same method is being applicable when you do the ARDL approach, when you do the vector autoregression approach, when you do the cointegration approach, or when you do the exponential smoothing, decomposition method, or when you work out with simple linear regression model as well. It's exactly the same. Okay. So we tested for the autocorrelation and partial autocorrelation of the error term for 211 and 311, and also the Porte-Monceau test for the white noise as well. Now let's do out of sample forecasting. Out of sample forecasting. Out of sample forecasting. And let me write ARIMA X rate, ARIMA 1 or 2 1 2 1 1. Right. This is what we have estimated. ARIMA 2 1 1. Predict. Oh, sorry. Sorry. I told you the method about the in-sample forecasting, but then I haven't prediction using Stira. So what we need to work out here first is since we are going to do the in-sample forecasting as well as out-of-sample forecasting, for doing out-of-sample forecasting, what first we need to do is we need to expand the range of the data so that forecasted values can be stored in the spreadsheet of the Stata file. Okay, so here it's like we are creating bigger chadar so that we can spread our leg further in terms of forecasting, just to relate with this problem. Okay. Expanding the database before forecasting. Let me call it expanding the database before forecasting. And the command, inbuilt command is tsappend add. So how many months in the future we are interested to forecast? Let's say we are interested to forecast for 24 months, right? 24 months. So add 12, right? Sorry, add 24. Right? It means it will be creating 24 observation additionally in our spreadsheet itself. tsappend, add 24. Or there is separate command. What you call is tsappend, last. Since we have the observation till January 2023, so 24 months, meaning it should be last 2025 month 1. And tsfmt tm. This is another command. It gives the same. 780 is already in the data set. Check in the Excel file whether how it's been generated. You can check out, right? So earlier we had the observation till 601. Now you find 602 till 625 additional months we have generated. Okay. Now in sample forecasting part 1. In sample forecasting part 1. So let's do, so let me just go with only one model right now. You can compare with 311 to 211. First of all, let me just work out with 211. And then, because when you model, your result should be pasted in the Excel file or Word doc file so that, comparison will be easy because all the results will be together in front of you. Okay. So 211 predict, predict X rate. So something has already been created. No. Okay. So E1 and E2 has been created. So now predict EX rate underscore E1. So that's the name we are giving for the predicted values. If P less than equal to PM 2023 M1. What are we doing? We are doing in-sample forecasting. Predict the exchange rate if the sample is still 2023 M1. We predicted, and after predicting, predict E2. Let me call it E3 because E1 and E2 is already there. So let me just to make consistency with P1 and E1, let me drop the earlier P1 and E1, E1 and E2. Drop E1, drop E2. So drop X rate underscore P1. Arima predict E1 residuals, right? We have already checked for AC E1, PAC E1, right? Or core gram, etc. We have checked, and the white noise we have already found out. So if you want to check how the forecasted values X rate P1 is looking like, right? So this is the predicted value, and this predicted value is the first difference value of the exchange rate. To get the level exchange rate value, you can simply give the command, because there is one command which I do not remember now. I'll cross check and get back to you in the next class. But when we talk about the first difference YT, it's YT minus 1 minus YT. So YT is actually equal to YT minus 1 minus delta YT, right? YT minus 1 minus delta YT. So with that, we can give the command gen level exchange rate is equal to lag of X rate minus X rate underscore P. And this is the level variable of forecasted, in sample forecasting. Okay? LBEX. Or just to have the consistent name, let me just drop it and give another consistent name, gen. Let me call it P1. Level exchange rate P1. Okay. Right. So this is in sample forecasting. We have generated. Now, other things we have already cross-checked. So if you want to plot and look at the actual value and predicted value, you can plot and look at, right? TS line, X rate, and level X rate underscore P1. You see, it's almost overlapping, right? It's almost overlapping. Actual value and the predicted in sample. Residual, root mean squared error, etc., you can find out because residual you have already calculated, or further, if you want to kind of find out the residual, you can call it R1. Res1 is equal to X rate minus level of the X rate underscore P1. Oh, it should be gen. Okay, so res1 residual has been generated. So from here you can calculate the root mean squared error. So summary. One of the way is to look at the summary. Res1. So yeah, mean, standard deviation, min value, max value. Standard deviation is like, square root of the root mean squared error. I mean, it's root mean squared error actually, close to that. So for this model, we have found out this. A similar fashion you can find out for the second model as well. Now, so in sample forecasting, we have done. So that's part one. Another one, in terms of looking at in sample forecasting, in sample forecasting part 2, and for this the command that you can give is ARIMA211, and X-rate, with X-rate I'll be giving the command if the sample that you are considering is from 1973 M1 to 2015 M12, let me write. Okay, so we are considering this to be a sample size, right? And we will be forecasting. Okay, we ran the command, then you write predict X rate P2 X rate P2 if P less than equal to PM, in the bracket we give 2023 M1, right? Within this only we want, even though we have considered the sample to be till from 1973 M1 to 2015 M12. So this generated exchange rate predicted P2. And this is again the difference. So the way we worked out in the earlier case, in a similar fashion, you can work out here as well. P2, log of exchange rate minus log of exchange rate. It should have been P1, right? It should be P2. Okay. Right. You can cross check in sample forecasting. So 7.88, 7.89. You see, in sample forecasting, there are slight differences in values as well, because in first case, we are considering the entire sample as the sample period, and then we are predicting to the same period. Now, in the second case, we are considering the sample from 1973 M1 till 2015 M12, and then predicting the remaining exchange rate for which values are already available. Okay,